Good morning, all of you MSc Physics student. So today we want to continue the first module of the energy study first subject, which is solar radiation and its measurement. So summary of the last lecture we have to see here. What is the structure of the sun, or what is the principal characteristics about the sun? That principal characteristics which is considered as mass of the sun, radius of the sun, density of the sun, or temperature or average temperature of the sun. Or after that we have to see here was last lecture by the rough structure of the sun, which is shown by different zone of the sun, which is considered as central core, photosphere, or out of this chromosphere, something that type, or which respect to that layer, or which respect to that core, or what is the layer which is there, what is the temperature of there, or what is the density of there. So that type of the principal characteristics was seen by the last lecture. In this lecture we want to see the next main point of this chapter, which is considered as the solar radiation, because this solar radiation or solar constant, because this point that depends on so how much the quantity of the solar radiation which is emit from the sun body and which is incident on the earth surface, and that depends upon this calculation data. We have to analyze how to harness the solar energy. So first of all, consider what is mean by the solar constant, or that is denoted by ISC. So that solar constant, which is nothing but consider as the total energy received from the sun, total energy which is received from the sun per unit time on a surface of unit area which is perpendicular to the radiation in a space just outside the earth atmosphere when the earth is at its mean distance from the sun. Okay, so we have to know that the diameter of the sun or diameter of the earth, and the concept of which is mean distance from the sun to the earth relationship. So when this earth which is at the mean distance, so that whatever radiation which is emit from the sun and which is incident on the earth atmosphere or absorbed on the earth atmosphere, so that the constant value of this solar radiation, which is nothing but the solar constant, and this value or approximately this value which is considered as, or which is calculated for the, or which is the recent measurement of the solar constant, that have the value which is approximately considered as the solar constant, which is 1353 watt per meter square. So this is the approximate value which is calculated by the calculation, and this value which is again considered as that 1353 watt per meter square, that is in calorie per meter square per minute, that is considered as 1.940 calorie per meter square, or that is 1165 kilocalorie per hour per meter square, and 4871 kilojoule per meter square hour. So that type of the different value in different units that stated here. And this solar radiation or solar constant, which is measured in terms of the solar flux or solar radiation intensity, or this solar flux or solar radiation intensity that leaving the surface of the sun, that is which is given as with the help of the Stephen's law or Stephen-Boltzmann law, or which is considered as that Hs is equal to sigma into T naught power 4, sigma into T naught power 4, because as this relation we have to get idea, so that this body which is considered as the black body, or that assuming as sun which is as a black body, and we have to know that that black body means that black body which has emits the radiation, emits the radiation, or that emits radiation which is absorbed the other body, and that emission of this more radiation which is considered as normally, or roughly say that the black body. And we have considered this statement in the solar constant, that sun as a black body, and that depends on this Stephens-Boltzmann law, and that law's mathematical statement which is considered here, that sigma into T naught power 4, and that sigma which is considered as the Stephens-Boltzmann constant, sigma which is considered as Stephens-Boltzmann constant, and that value which is considered as 5.670 into 10 to the power 8 watt per meter square, Kelvin power 4, or average temperature on the surface which is considered as T naught is equal to 57 into 62 Kelvin, degree Kelvin. So that is the average temperature of the sun, and this is the Stephens-Boltzmann constant. And if we want calculate this value Hs, so multiply this value and doing the calculation, so that Hs which is considered as the sigma value already given here. So what is value? That is 5.670 into 10 to the power minus 8 watt per meter square, Kelvin power 4 into T naught power 4, or average temperature that is given. So that is considered as 5762 degree Kelvin power 4. So that calculation which is here, and roughly calculated this value which is given here, 5.961 into 10 to the power 7 into 10 to the power 7 watt per meter square. So that huge amount of value of which is here, and depends on this calculated value we want to calculate the final solar flux value. Consider as the total radiant power emitted from the sun which is obtained by the multiplying the above calculated by the surface area of the sun. So that is mean by, if we want to calculate the power which is radiant energy from the sun, so that radiant power which is calculated by, so this Hs value which is multiplied by the surface area of the sun, or you have to know that surface area, because we have to consider that the circular sphere or sphere value or consider as the sun, and we have to know that area of any circular or circumference value which is considered as the 4 pi r square, and r value of the sun, that already we have to know that. So that here we want to calculate the radiant power energy value, so that is considered as the P naught, So total radiant power which is considered as total radiant power, that total radiant power which is considered as that P naught is equal to this value Hs into surface area of the sun which is considered as 4 pi into r square. So here Hs value which is considered as 5.961 into 10 to the power 7 watt per meter square, okay, into the value which is given here 4 pi r square, and that radius of the sun, that value we have know, that is 6.960 into 10 to the power 8. So that is here 4 pi into 6.960 into 10 to the power 8 meter. Okay, because of the radius of the sun, which is given here 6.960 into 10 to the power 8 meter. Okay, and this value which is put here, and that roughly calculation this which is given by that P naught is equal to 3.630 into 10 to the power 26 watt. So that is the power unit. You have to know that that is the watt, and this total radiant energy in terms of power, or total radiant power, which is here calculated by P naught is equal to 3.630 into 10 to the power 26 watt. And if you have to consider that sun emit the radiation isotropically, and this enormous power which is called as the luminosity, so that is mean by that is the radiation which is emit from the sun for the isotropically. So this power which is called as the luminosity, and that the intensity which is varies from the square of the distance from the center of the sun. Intensity varies from the square of the distance of the center from the sun, and that distance which is considered as small r. Surface area of the earth which is considered as, we have to know that 4 pi into small r square, and radiant flux enclosing the such surface which is given as. So we want to calculate here the radiant flux, and that radiant flux which is denoted by H naught, and that H naught which is considered as, so radiant flux crossing surface, crossing the surface which is given by that H naught is equal to, that H naught is equal to P naught upon 4 pi r square, P naught upon 4 pi small r square. Or we have to get idea this what is the this 4 pi P naught, that P naught is equal to Hs into 4 pi r square, so which is considered as Hs into 4 pi r square divided by this 4 pi small r square. So we have to say see that here, so that 4 pi is there, 4 pi is there, so that 4 pi terms which is get cancelled. So what is remaining? H naught, that is the radiant flux which is given as Hs into capital R square divided by small r square, capital R square divided by small r square. And if we place the value which is here, so consider as this Hs value, what is the Hs value which is given as 5.961, 5 point, or calculate for the last which is considered as Hs value 5.961 into 10 to the power 7 watt per meter square. Or we have to know idea about the radius of the sun which is considered as 6.960 into 10 to the power 8 meter, or which is square here, so that's why square here, and divide by small r square, divide by small r square. And that unit for this radiant flux H naught which is equal to watt per meter square. Watt per meter square. So, that is because the earth distance from the sun, that is considered as sun earth mean distance or mean distance, which is the relationship between the sun earth, and that distance which is denoted by small r, and that r which is the value 1.5 into 10 to the power 11 meter. So this r which is what the mean distance between the earth sun. So where r is equal to mean distance of sun earth relationship. Okay, and that this r value which is given as here 1.5 into 10 to the power 11 meter, 10 to the power 11 meter, and this flux or intensity radiation which is calculated with the help of this H0, because this calculation which is given roughly value consider as 3.044 into 10 to the power 25, and this value which is put here, so that we get the value of the radiant flux. So that radiant flux value which is given here, so that H0 is equal to that value 5.961 into 10 to the power 7 into 6.960 into 10 to the power 8 whole square, that calculation which given here, so that is 3.044 into 10 to the power 25, or divide by this r square, and this r value which is nothing but 1.5 into 10 to the power 11, so that is given as 1.5 into 10 to the power 11 or meter square, that is the whole square, and that H0 value which is given as 1353 watt per meter square. So that H0 is equal to 1353 watt per meter square, and the value of the flux is called solar constant. The value of the flux is called solar constant. Okay, so once again summarize this point. So what is mean by solar constant? So that solar constant which is defined as the total energy which is received from the sun per unit time per unit on a surface of the unit area which is perpendicular to the radiation in a space or which is just outside the earth atmosphere when the earth is at its mean position from the sun. And already see that what is the approximate value of this solar constant, which is approximately calculated, which is considered as 1353 watt per meter square, or this value which is calculated by doing the just simple calculation, and this value which is calculated, that is 1353 watt per meter square, or this flux value that is radiant flux which is given here, and this value or this radiant flux which is considered as the solar constant. Next main point which is calculate here, we want to interesting the calculate here. So what is mean by the angle divergence, that is the angle divergence, and this angle divergence, which is nothing but the variation of angle, that is delta theta, that is variation in angle, and this is which is considered as 2r, 2 into capital R divided by small r, and that 2 into r, that is the radius of the sun, and small r, which is considered as the mean distance of the earth from the sun, so that is which is considered as 2 into, that is radius of the sun, which is considered as 6.960 into 10 to the power 8 meter, divided by this value, which is considered as 1.5 into 10 to the power 11, 1.5 into 10 to the power 11 meter. So meter or meter. So if doing this simple calculation, so that roughly value which is considered here 9.28 into 10 to the power minus 3, 9.28 into 10 to the power minus 3 radian, minus 3 radian, and this which is considered in the degree, so that is 0.53 degree, 0.53 degree, or which is considered as 32 minute. Or consider as 32 minute. Okay, 32 minute. So that is the calculation of the angular divergence, and that angular divergence, which is 0.53 degree or 32 minute, which is considered as slightly more than half degree, which is slightly more than half degree, slightly more than half degree, so that the flux making the solar constant can be approximated as the monodirectional radiation. So depends on this calculation, we have to say that that is monodirectional radiation, and we have to know that the idea that earth which is revolves around the sun once in a year in an elliptical orbit, and that orbit which is considered as the nearly equal to the circular orbit, and that the intensity of solar radiation I that reaches on the earth, and this can be approximated by the equation. So that is given as, or before that we have to see here the small concept. So that is here the divergence of angle, or the divergence angle, or angle of divergence, which is through the sun, which is large substance to the angle, which is considered as 32 minute or 0.53 degree at the earth surface, to that the making the angle. And the next point, that intensity flux or intensity of solar radiation, which is I, which is considered I incident on the earth surface, and this can be approximated, which is considered as the relation, which is I upon ISC. So that is considered as I upon ISC is equal to I upon ISC is equal to 1 plus point not 0.033 plus cos of 360 into n minus 1, 360 into n minus 2 divided by total number of days in the year, that is 365, and that relation which is will be become here, so that is 1 plus 1 plus 0.033 cos 360 into n cos of 360 into n divided by 365 divided by 365. So that is n is the day of the year here. So this is considered as ISC, or by doing the last calculation, that solar constant H0, which is considered as the 1353 watt per meter square, this value and this formula which is also same. So that is here n is equal to, which is considered as day of the year, and putting for this value whatever n, which is day number of the year. So we have to get according to this day, so we have to get the idea of the solar constant. So this is the information about the solar constant, or how much radiant energy which is incident on the earth surface. Okay, so now next lecture we want to see here the electromagnetic energy spectrum, because which is the electromagnetic spectrum or radiation, which is usually divided into the wavelength band, and that is, we have to know that the types of the name of the electromagnetic spectrum, that rays considered as the cosmic rays, gamma rays, X-rays, UV ray, that is ultraviolet rays, visible light ray, infrared rays, radio waves. So that spectrum and that range or wavelength which is see in the next lecture. And after that, the solar radiation of the earth surface, so that is what is mean by the terrestrial solar radiation, what is mean by extraterrestrial solar radiation, which is see in the next lecture. So thanking of you.